Good evening, everybody. So welcome to the second day of the short-term course. So the second day starts with the same where we continued from the same lectures where we continued yesterday. It will be delivered by Professor Maruko. The first lecture titled as Ionic Liquids and Polyionic Liquids for Carbon Dioxide Separation. As before, we will take up questions at the end of the lecture. So I'll now request Professor Maruko to kindly start the lecture.
Hello, Professor Tamal.
Thank you.
Thank you again for having these seminars. I hope that they are useful for your students.
So
and so today I'm going to change subjects and talk a little bit about gas separation, in particular CO2 separation, for this talk. What I'm not going to change is the materials. So here we are still going to use ionic liquid-based materials, and I'm going to show you how we can use ionic liquids and polymeric ionic liquids for carbon dioxide separation. I don't have to tell you that we are fighting CO2, the emissions of CO2, and we have to do something about CO2 and to obey all those strict rules that are now being enforced. We know that our climate is changing. We know that we have a lot of problems with the climate change, not only because the Earth's atmosphere is becoming hotter and hotter, but also there are also other problems associated with it. The rising of the sea level, the lack of rain is also very problematic in some countries that really depend on agriculture. And though this is a big question, it is also a big question when we talk about energy production. Most of our energy comes from fossil fuels, and the burning of fossil fuels is one of the main responsibles for this great enhancement in CO2 in the atmosphere, let's say it this way. However, there are a lot of more relevant CO2 separations, not only CO2 from flue gas, from post-combustion, but we can also have the production of, for instance, biohydrogen, that I'm also going to explore a little bit here, for energy. Right now, I think that the whole world is talking about hydrogen and the hydrogen production, and we can produce hydrogen from syngas, which demands very high temperatures and very high pressures. And while we do not get there with polymeric ionic liquids, I'm here going to talk a little bit about biohydrogen production that is actually produced by microorganisms in aqueous environments. The conditions are very mild. It's room temperature and atmospheric pressure. And there's been a lot of efforts from the biotechnology companies to really produce biohydrogen, and thus the need to purify the biohydrogen. So we are also going to focus here on CO2, H2 gas separation. So we have here the production of biohydrogen, the conditions. We can see that its major contaminant is CO2, and those are the temperature and pressure that I mentioned to you. When we talk about produce hydrogen from syngas, so the compositions are a little bit different of the stream that we want to purify, But as you can see here, this is usually produced at 200 degrees C and around 20 to 25 bars. And so here we are going to focus more on biohydrogen operating conditions. And then, I mean, it would be the same to apply it to shift syngas. Okay. So in terms of reducing the CO2 emissions, as I was mentioning to you before, there are 3 points where we can decrease the CO2 emissions. One of them is in the post-production, so it is in the flue gas from power plant streams, and the separation that is here involved is CO2N2, is in the CO2 separation from syngas in hydrogen production, which means also biohydrogen at mild conditions. And then it's the natural gas sweetening, where the gas pair to separate is CO2CH4. We will not talk about this one here today. I've showed you before the conditions for the biohydrogen. So now here I'm showing you the conditions for flue gas. We operate between 35 and 120 for flue gas and 1 bar of pressure. And then either the recovery of hydrogen from syngas stream or natural gas are typically done at higher pressures, and production of hydrogen from syngas at higher temperatures. Okay. So the compositions are also somehow different, and so we really need to focus on a feed composition and different experimental conditions. Okay, so what do we have for the CO2 separation nowadays? These here are the 3 most used technologies that are nowadays used for CO2 separation. There is no doubt that the most used technology is solvent absorption, typically using amines to capture the CO2 through the reaction to produce a carbamate. The disadvantage is that this reaction has been so much tuned, the interactions are so strong, that then it's very energy intensive when we come to desorb the CO2 and recycle the amines. In the literature, there's also been a lot of efforts to use adsorption methods. In literature, and not only in literature, cement plants that also produce a lot of CO2 have been preparing adsorption materials to capture the CO2. And these adsorption materials are typically they can be as simple as activated carbon, or they can be as complex as metallic organic frameworks and other inorganic materials that have been coming up in recent years. The problem is this adsorption is really chemistry tailored, the materials. It's chemistry tailored. So they are porous solids, and we cannot still control the size and the size of the pores, and thus the costs of the preparation of these adsorption materials. Some of them are very effective, but they are very expensive and very fragile, which prevents their use in industrial applications. This leaves us with membranes. Membranes have a lot of engineering advantages. Since they are compact, they have low operating costs, and they are less energy intensive. However, membranes have not been very much explored, and so what is known about membranes is still not enough to implement industrial processes, at least for CO2 separations, and this is what we've been working on. Okay. When we talk about membranes, now we need a material to prepare the membranes. And the materials or the solvents that have been most used recently are ionic liquids. And when I compare ionic liquids with the liquids currently used for absorption in an absorption unit in industry, which are amines, the amines have to start with a big disadvantage because they have high vapor pressures, and we lose a lot of the material, of the solvent to the atmosphere. On top of that, they are also very corrosive, and this is a big disadvantage. So here we have ionic liquids that in terms of their efficiency, as I'm going to show you in a little bit, towards CO2 separations, gas separations, the main advantage is their negligible vapor pressure. So I can bubble the gas and no ionic liquid is dragged outside. They also have a high thermal stability, and so they can be used at much higher temperatures than the amines. Okay, so what makes these ionic liquids unique for CO2 applications? To start with, their tunability through the combination of different cations and anions. We said yesterday that there could be more than 1 million ionic liquids ready for us to be prepared. Then the possibility of even further tuning by introducing functional groups in those commercially available ionic liquids. And last but not least, we can also play around with different mixtures of ionic liquids. Okay, so we have published a paper on the ionic liquid-based materials to separate CO2. And now a recent review just came out also how to use adsorption materials together with ionic liquids to improve the performance of carbon dioxide membranes. So we can have, when we use ionic liquid-based membranes, we can have 4 different configurations. We can have supported ionic liquid membranes, and here I get a porous inert support, and I support the ionic liquids inside of the pores of the membranes. So this is very easy to do, but it has some problems, as we'll see. The other approach is the gelled ionic liquid membrane. So we just pick an ionic liquid and use a gelator or a polymer and prepare membranes. The thing is that the compatibility between the ionic liquid and the gelator or the polymer is crucial to incorporate a large amount of ionic liquid inside of these membranes. In third place, we have polymeric ionic liquid membrane, polymer ionic liquid membranes. So we get a common polymer and we put ionic liquid inside. So more polymer than ionic liquid, and here it's more ionic liquid than polymer. Again, stability issues now. The compatibility issues arise here if I want to incorporate a large amount of ionic liquid. And to solve this problem, we can use polymeric ionic liquids, because here the compatibility between ionic liquids and polymeric ionic liquids will be much larger, and thus I can incorporate a higher amount of ionic liquids. So here I'm going to talk about these two, the supported ionic liquid membranes, SILMs, and the polymeric ionic liquid membranes, PILIL membranes. Okay. So what I'm going to do I'm going to show you now some examples where we use the ionic liquids in supported inert supports. Okay, so one of the ionic liquids that we first did, and this was to aim at we used collinium carboxylate. So the collinium cation is biodegradable and is non-toxic, and we wanted to see how it would perform. And here we have with several carboxylic acids. So these ionic liquids were prepared in our lab. So they were all combined with the imidazolium cation, and here I have several families that we have prepared. So we have prepared the acetate lactate, so with acids, with NTF2. We have also studied the cyano groups. We are going to see in a little bit that the cyano groups are very nice because they have very low viscosity. We also used the sulfate, the methyl sulfate, ethyl sulfate. And again, in order to become more compatible, we have tested amino acids. Okay. Another study that we have done more recently involves a different type of ionic liquids, and these were done very specifically for us. These ionic liquids have been, so NTF2, as I mentioned to you before, and other fluorinated anions are very used for CO2 capture, because everybody knows that fluorine is very CO2 philic. And they provide ionic liquids that have low viscosity and low melting points. So one of our collaborators tried to have the best of both worlds and tried to combine in the anion several functionalities. Like, for instance, in this anion here, we have a combination of a little bit of NTF2 and a little bit of cyanoamide. Here, I just have the fluorines. Here I have half is NTF2, the other half is a sulfonate. And here I have this anion that is more fluorines than the other ones, just for us to see how it would behave to introduce a symmetry in the anion or to have longer fluorinated chains in the anion. Okay, so this is how we prepare the films. So this is our setup. We just drop the ionic liquid sample on the membrane and we spread it and we vacuum it for 1 hour so that the ionic liquid really penetrates in the pores of the inert support. And this is the result that we get. So the ionic liquid is fully impregnated in the membrane. We can see this here in the naked eye because it's yellowish. What we do is a gas permeation tests. In a permeation cell, we have a time lag apparatus that allow us to measure simultaneously permeability and diffusivity. Our membranes that I'm going to show to you today are dense membranes. It is very difficult to have porous membranes to separate gases. We know that to separate liquids, we typically use membranes with different pore sizes so that the solutes do not pass all at the same time these pores. However, gases have very similar diameters, and it is very, very difficult to have a porous membrane for gas separation. In terms of polymers, I would say it's still not possible. So our membranes are dense. We are going to measure permeability and diffusivity, and we are going to take solubility. So we assume that the diffusion solution mechanism exists. What is this? This means that the solute, the gas, first dissolves into the membrane, then diffuses along the membrane, and then desorbs on the other side, which means that the sorption step or the affinity of the ionic liquid for the gas is very important, but the diffusion, the fast diffusion of the ionic liquid inside of the membrane is also very important. So we would like to incorporate as much ionic liquid inside of the membrane as we can so that we have a fast diffusion. All the data that I will show you here today were measured at 20 degrees C and 1 atmosphere, because this is for comparison with all the other membranes published in the literature in the Robson plot. So what is the Robson plot? The Robson plot is this plot that you are seeing here. It represents, it's a log plot again, and it represents the selectivity of CO2 towards N2 as a function of the permeability of the most permeable gas in this pair, which is the CO2. What Robson did, it was to collect a large amount of data from literature, and that allowed him to draw this line here. This is a line in 2008. And as we can see, here we have all the experimental data that the people have been measuring with other supported ionic liquid membranes. And here it starts to appear our data. Okay. So this is the most environmentally friendly ionic liquids, the collinium with acids. As we can see, these are very viscous, and by being very viscous, they have low permeabilities, and they do not overcome the upper bound, which is where we want to be. They fall here in this region of very low permeability. Then we have, in order to decrease the viscosity, what we did is we got those ionic liquids with acids and we mixed them with NTF2, that is very little viscous. And here we have the mixtures of ionic liquids, lactates with NTF2, and we can see that the permeability greatly improves towards a higher permeability. And there are even some members that surpass the Robson plot upper bound, which is where we want to be. Now, in what concerns the cyano groups, you can see that the cyano, here are the cyano anions. We can see that some overcome the Robson plot, and this is for the different quantities of the ionic liquids. And that CCN3, so tetracyanometane, provides very nice results. And tetracyanoborate also provides very nice results. So these are the first results that are really excellent. Okay. In terms of the anions that I was talking to you about before, so instead of making mixtures, we just have in the same anion the two functionalities, the symmetric anions, as I call them. We have here the TEF-sum, and we see that the TEF-sum is also very non-viscous, and that is why it also surpasses there the Robson plot. However, there is no big difference between the TF-sum and the FSI anion, especially due to their low viscosity. So we have seen that this is a very promising strategy to separate gases. It can be tuned just by mixing different cations and anions, and we can have very good selectivities also. However, there is a disadvantage, and the disadvantage is that the ionic liquid phases inside the pores through hydrophobic interactions that are weak, which means that if we have a higher gradient, the ionic liquid can be displaced from the membrane, and thus we lose our separating fluid. So in order to overcome this disadvantage, we proposed to prepare polymers. So if instead of having ionic liquids, I will have polymeric ionic liquids, they will have high thermal stability because polymers have high thermal stability, high chemical stability, and high chemical flexibility because I can just polymerize any ionic liquid. The disadvantage that I have when I prepare membranes with polymeric ionic liquids is that now I have a solid. And by having a solid, I have a substantial drop in the gas permeability when I compare it to supported ionic liquid membranes. So what we did, it was to blend the polymeric ionic liquids and the ionic liquids and form composite membranes. In this way, we can have the mechanical stability of the polymeric ionic liquids and the conductivity of ionic liquids. Realize that the ionic liquid here does not leach from the membrane because the ionic liquid has intimate coulombic interactions with polymer. It acts as a polymer stabilizer, and so we don't have those instability issues that we have in silks. Okay, so typically what we do is we prepare these membranes by solvent casting. I told you that they were dense membranes. And so here we have the polymer. We are going to see that we have used some commercial polymers, but we have also designed some polymers. Having the commercial polymers has one big advantage, that is, we have a fixed molecular weight. We can buy with whichever molecular weight we want. And to prepare membranes, robust membranes, it is very important that the molecular weight of the polymeric ionic liquid is high. The polymeric ionic liquid that we use here is around 200,000. So this is how we prepare our dense membranes. We use the solvent casting method. We just dissolve the polymeric ionic liquid and the ionic liquid in a solvent, and then let it to evaporate very, very slowly. Typically, the solvent is acetone. It is very important that the ionic liquid and the polymeric ionic liquid are compatible. So typically, we choose ionic liquids that are very similar to the polymeric ionic liquids. Okay, so we had different approaches when we started working here. We have explored just like in ionic liquids. Here we explored also different cations. Different cations. We also did some with pyrrolidinium, and I'm going to show you why we did this with pyrrolidinium. And we evaluated the amount of ionic liquid that we put inside of these pyrrolidinium membranes. And finally, we used the cyanoanions that we checked that were also very good in films. So we prepared these polymers here with the most important cations from the ionic liquid toolbox. We did it by free radical polymerization, and then in the end, we doped our polymers all with the correspondent ionic liquid. 10% of the ionic liquid inside of the polymer. Here we wanted to see more the polymer backbone and not the ionic liquid. This was just to make the membrane not so brittle. Okay, so here we have the results for the gas permeability. For the gas permeability, we have here, let me go back a little bit forward. We have here our membranes. So we can see that the collinium perform, although they are much more biocompatible and biodegradable in terms of performance, they are not very good. Then we have here the ammonium cations that we were talking about yesterday that have the charges very screened because of the chains. They also do not perform very well. And those that perform really well are the pyridinium, those with pyridinium cations. However, so this is the impermeability, and realize that the same trend is obtained in diffusivity. Now realize one thing, is that these pyridinium-based membranes are those that provide the best results, but we did not pick them up to continue our studies. What we picked up was dimidazolium, because, it was the pyrrolidinium, because in the pyrrolidinium we can buy them. And if we buy them, so we always know the molecular weight, and we know that we want a high molecular weight and a fixed molecular weight to take out the effect of the molecular weight from our equation. Okay, so typically what we do is we buy a polyelectrolyte, like the polydiallyl dimethylammonium chloride, and then we just exchange the anion with an anion that we know it's CO2-philic, like for instance the NTF2. And this is the strategy that we are going to follow from now on. So just buy the polymer backbone and then use ionic liquids, salts with anions derived from ionic liquid to do the anion exchange and to prepare the polymer. Okay, so in this work, we tried to see how our polymeric ionic liquids behave when we add more ionic liquid to them. So here we went from 100 pure ionic liquid to pure pill to pure ill. Here we do not have any polymer, and this 100 means that we have all ionic liquid. These two with the highest amount of ionic liquid, we could not prepare. The last one, it's understandable, but the 80% of ionic liquid, we could not prepare it as a freestanding membrane because it breaks down, it is very jelly, and so we supported these as we supported films. So we prepare here with this pill 80% ill. It is a liquid. We prepared exactly as a film, put it into a membrane, and allow the solvent to evaporate. And the results that we are here watching are from those polymers, and we got exactly what we thought we would got, which is that the highest amount of ionic liquid, the highest gas permeability I have. Diffusivity behaves the same way. You can see here how the polymeric ionic liquid is not very good. And so the polymeric ionic liquid should only be thought as a support for the ionic liquid, because really what really separates is the ionic liquid. Okay, and this is what I told you, that they increase with ionic liquid incorporation, and this leads to a lower gas resistant diffusion. Okay, so in another attempt, what we did, it was to use mixtures of anions, just like we did before. So here we used some fluorinated ionic liquids also, NTF2, and the rest are different anions. So we can say that here we have copolymers, because we have one polymer with the NTF2 and the other polymer with the other functional anion. And here we dope them with 20% of ionic liquid, because from the previous results, it showed that 20% was the best amount of ionic liquid to have inside of the membrane, at least for mechanical properties. So here we have the permeability results for CO2, methane, and nitrogen. We can see here that this in blue has very good permeability. And this is where we have the anion of the NTF2 with the dodecyl sulfate, which is a surfactant. Typically, it's a surfactant. So what we think is that this long alkyl chain of the dodecyl sulfate creates free volume inside of the pores, and thus allows for the gas to pass through. Sometimes there are some counter anions, like for instance, the PF6, that decrease the permeability of the polymeric ionic liquid. Okay, another strategy that we did, again with the pyrrolidiniums, was to exchange the anions, the chloride anion of the polyelectrolyte by other anions. Here we did the cyano family with 2 groups, 3 groups, and 4 groups. These ionic liquids used to be sold by Merck. This was a collaboration between us and Merck. The problem here was that it was quite difficult to prepare these membranes. The membranes that I was telling you about, they are very easy to prepare just with a solvent and a petri dish. And here, these were very difficult to be prepared. Some are very brittle or jelly even, and so they cannot be prepared. In fact, all the BCN4 were like that. I think that we measured 1 or 2, but we could not measure more because they just break apart. Despite that, all of these composites are homogeneous, with 60% of ionic liquid incorporated. And so those are the ones that we are going to pursue. In order to tune a little bit the ionic liquid, the efficiency, we added ionic liquids. The same ionic liquid was added to the same membrane with the same anion, but also mixtures were done in order to see if it was important to keep the structure, the chemical structure, if it was just the chemistry that mattered for the membrane stability. And this work was done by Raquel Santos that worked in our group. And so here we did a lot of these membranes, and although, as you are going to see, they perform quite well, they are very difficult to be synthesized, and it is very difficult to incorporate high amounts of ionic liquid. We have 3 that are good, and the other 2, they are not good. The other 3 are not good. Okay. So here we have the permeabilities. We only managed to have to be able to measure the anion BCN4 inside of CCN3. These are all with the different cations and anions. As you can see here, I have this polymeric ionic liquid, but I cannot put 60% of ionic liquid inside of it, but I can put 60% of 3-cyanomethane. So sometimes these cyano groups are very difficult to work with due to the geometry of the anion that is not very flexible, is very stiff, so it is very difficult to work with. Okay, so we are ready for results analysis. Here we have the pills with the colinium, are those in purple. We can see that the pill with the colinium is not very good. With 10% of ionic liquid is not very good, is in fact a very low permeability due to the high viscosity of the ionic liquid. Now here in orange, we have the mixtures of anions. We can see when we compare these 2 works with each other, it is more advantageous to play around with the mixtures of anions than to check on the cation. So which means that the cation here in purple are less important than the anion in terms of permeability effects. Here we have the from polymers to ionic liquids. And so from polymers to ionic liquids, we can see that this is 10, this is 20, this is 40. So this is the strategy to blend ionic liquids inside of a polymer that really displays or increases more the permeability. No major difference you can see here from the 80% and the 100% of ionic liquid. So despite these are quite good results in terms of permeability, we cannot shift very much the selectivity. They are all here under the Robson plot. However, when we use the cyano groups, this changes. The cyano groups are much more selective than the NTF2. And so when I add larger amounts of ionic liquid, I can have high permeability compared here with this with NTF2, high permeability and high selectivity. And when I have 60% of the pill with CCN2 and 60% of ionic liquid, it surpasses the Robson plot upper bound. So these were the other ones that we did the mixtures. This is here in light pink. Are those with the mixtures of the anions. So they are all here around in the same order of magnitude and all above the Robson plot, which is very good. So the cyanoanions are those that are the most promising anions. Now I just wanted to show you the performance of the other ionic liquids, the other polymeric ionic liquids, let's say. And here I go for, these were done, are those that were done that I showed you right now. But now we checked in gas mixtures. As I showed you before, the CO2 and N2 are not alone. And so we are going to complicate our problem. We are going to introduce hydrogen, CO2, and nitrogen at the same time, simultaneously. And the results we did this at several temperatures and several feet pressures. And the results are here, but possibly we can discuss them in terms of Robson plot. And here they are. Let me put all these. Okay. So here we have for CO2, hydrogen, the separation, and this is several temperatures for instance, the polymer CCN3 with 60% of ionic liquid. So the increase of temperature greatly decreases the selectivity, which is a pity because it means that we cannot work at higher temperatures. And here is the effect of pressure. We can see that the effect of pressure is much less pronounced than the effect of temperature. And we can see that here also in the NTF2, and we can see also, I'm sorry, NTF2 is this one, in NTF2, 40%, and NTF2, 60%. Effect of pressure, and here effect of temperature. So this means that these materials are very nice for biohydrogen because I'm here, I have a high selectivity for them. But when I go to do, for instance, syngas, and we lower the temperature to around 100, although our polymers are still above the Robson plot upper bound, they are much less selective than before. Another strategy, very recently, so this is submitted there, but it was published, I think, last month or something like that. It was to use networks, to use polymer networks to incorporate the ionic liquid inside. So we use the polyethylene oxide, polybutadiene rubber network, and then we incorporated the ionic liquid. So the ionic liquids that we chose, of course, were those that gave us the best results from previous tests. And you can see here our networks, they look quite good. Some of them, we just did the solvent casting of the network. So we prepared the network with the ionic liquid inside. But another strategy is to do the post-swelling. So we have the network, and then we swell the network, and we put the ionic liquid inside. That also works quite well. So these are the two strategies. In the first one, the ionic liquid was incorporated directly when we prepare the network. In the second one, we have the network, we make a solution with the ionic liquid, and the ionic liquid gets trapped inside. And this last strategy proved to be much better than the previous one. So now I'm just going to show you these results. So what here we have are the mechanical properties. Mechanical is important. It shows that these membranes are more flexible than the polymeric ionic liquid membranes. We knew about that. So we have them here. The polymeric ionic liquids are more brittle than these networks. although the network separately works really well, as you can see. Okay, so what about results? Here I have the performance. So as we mentioned before, these are all single gas results that we measure in our time lag. We have here the membranes with the asymmetric anions and all the other membranes that we did, the mixed gases here. And this is what we get from the networks. So this is the pill-hill polymer, and this is the incorporation of 60% of the same ionic liquid inside of the network. So when I just use 20% of ionic liquid with the asymmetric anions, I have this big change. When I use the same, the corresponding anions, so you can see that this strategy is really nice to increase the permeability, because the amount of ionic liquid is increased inside of these networks. And these networks are not very difficult to prepare, and they do not even contain ionic liquid. Okay, so what are the results? The results, the conclusions. The conclusions is that the preparation of pill-hill is very promising. We can really tune it with different polycations, different counteranions, mixtures, and so on. The results for the separations are also very promising. So where do we want to be right now? We want to be here on the Robson plot always, but still these fluxes are not competitive enough. So we have very selective materials, but our materials are not very permeable. So right now what we are doing is trying to come up with new strategies to increase our permeability. Okay, and with this I just finished. Thank you very much, you all, for your attention.
Okay. Okay, thank you, Professor Marcos. So time for some questions. So, okay. Okay, there is one question. Should all the ionic liquids containing fluoride groups prepared in plastic or in glass apparatus?
I guess that the person that asked that is concerned about the composition of the anions in the acid, that's in acidic regions. I don't know. We prepare them all in glass. We use Petri dishes in glass. We never use plastic, because when you scrap the plastic, when you're taking out the membrane, we can scrap plastic and take plastic out. So we use glass all the time. And all these anions are very stable anions. So we perform always routine tests with NMR, and we never saw any contamination.
Okay. Any other questions from others? They can put their hand icon. Anybody from the participants? Okay. Okay, I have one or two questions. That is, when you prepare this, wait a second, there's some echo, I think. Wait a second. Yeah. Can you hear me now?
Yes.
Yeah. So when you prepare these polyionic liquids, I am concerned, is there an opening of the ring or the imidazolium ring during your permeation experiments? Because you know, these rings, ring opening, does it happen?
We don't think so. No, I don't think the ring opens. I think it is very stable. You say that when I prepare the pyrrolidiniums, The pyrrolidiniums, we do it not by ring opening, but by ring closing. Yes, in the first set of polymers, yes, we prepare them like that by ring closing. Then we decided it is very difficult to prepare polymeric ionic liquids for the preparation of membranes because the molecular weight is not high enough, especially in the lab. So all the times that we prepared, we got polymeric ionic liquids around 80,000. And 80,000 is difficult to cast a membrane with a polymer of 80,000. And so we decided to go and always buy the backbone. So our backbone is always a cation because cation has less impact in the selectivity. And we just buy it because when we buy it, we know that they offer us 3 molecular sizes, and we always choose the highest molecular weight that they have, and that imparts membrane with a much larger stability, mechanical stability.
Okay, and what about these glass transition temperatures? How are these values? That I'm just maybe you have presented. I missed out. Maybe.
No, I did not present the thermal studies because I thought that the thermal studies would be very lengthy if I present here the thermal studies. I don't remember very well the glass transition temperatures. I know that the glass transition temperatures, for instance, it really depends on what you're working. We have the CCN3 ionic liquids, based ionic liquids. We cannot see in the range that we are doing. We cannot see any glass transition temperatures or any melting.
Okay, fine. So thank you again. Any other questions? Okay, I think there are no other questions. Then we can move to your next lecture. Next on the concluding lecture.
Okay, let me close this and open the next presentation. Okay. Okay, can you see it?
Yes, I can see it. Yes.
Okay. Okay, so today I did a little bit shorter talks, so that are probably more direct to the point. But if anybody does not want to ask a question, but wants to send an email, I will be glad to answer and to engage in discussion. So, this topic that I'm going to show you now, it's very different from the one that I presented. Very different and very similar. The materials are going to be the same, but we are going to use it for solid phase microextraction. I don't know if all of you are familiar with solid phase microextraction, but it is a powerful sampling technique that allows us to concentrate analytes on polymer coating. So in fact, what I have is, if I think about it, I have some sort of a plunger, and I can, when I click on top, the plunger exposes a needle, and on the top of the needle, I have fused silica that is coated with a sorbent. So here I have the silica and here I have the sorbent. okay, the solvent should be here, only in this part, in the last 2 centimeters. So this looks like a pen or a small syringe. And this is done today typically to evaluate anything that is present in very small concentrations and that we cannot evaluate with our current analytical techniques. So this serves to concentrate samples and to analyze samples in, for instance, a GC or a GC-MS. They are typically used in food and pharmaceuticals to sample food and for instance in fruits it's very well known to see if the fruit is ripe or not. They do that. In pharmaceuticals it's also the same. There's been a lot of wildlife study just by using this technique also of solid phase microextraction. And typically the way that it works is that, for instance, think about this as our sample. The sample has some vapor pressure. It is inside of a closed vial. So I have the plunger here. I use the plunger to perforate the septum. And then here inside, I expose the fiber. And the fiber is going to sort analytes from the headspace of the sample. So this is a non-destructive sampling technique. Then I take the plunger out of the flask and I desorb it inside of the GC column. Okay, so there are companies, chromatographic companies that sell us these septums, and of course that there are different septums for different analysis. What you could probably think is that there are a lot of materials that have already been incorporated in these microextraction devices, but in fact that is not true. There are very few polymers that have been used to prepare these coatings, typically PDMS, PA, polyacrylic acid, and DVB. And right now we have all of these with carbon inside also to create porosity effect. And so basically this is what we have to analyze everything that you name it to analyze. And our idea was to use polymeric ionic liquids to prepare these fibers. And why would we use polymeric ionic liquids? For the reasons that I mentioned before, because they have high thermal stability, low vapor pressure. This was the first time when they were introduced, when the ionic liquids were studied for SPME, they were studied as ionic liquids. So they have high thermal stability, low vapor pressure, non-flammability, and tunable properties. And so I can make combinations 10 to the power of 18 of all these cations and anions, and we can prepare fibers that can be tuned for all the analytes that I want to desort. What the people realized when they used ionic liquids is that, as I mentioned before, this needs to be desorbed inside of the GC. It is desorbed typically with temperature, and as the temperature increases, the viscosity decreases, and so it is the ionic liquid will just drip inside of the chromatographic column. And so this was not a good idea. We decided to do polyionic liquids. And in polyionic liquids, the idea was to coat the tips of the plungers. So we bought some commercial plungers. We scraped the tips of it, and then we just put there or absorb there our polymeric ionic liquid. And we wanted to see the sensitivity and the limit of detection and the selectivity of our fibers. Typically, this is already done. Some methods similar to these have already been done. Some polymers that are very specific have already been done, for example, for the detection of ethanol. When the police stops you, I don't know how it is in China, but it should be the same. When the police stops you because you're driving and they give you an ethanol test, a breath test, what they use is a fiber that really catches ethanol. We also know that there are a lot of other things that can be detected by breath analysis, especially in the medicine field. For example, if we test nitric oxide in our breath, it means that you're looking for asthma. It has been reported that acetone is for diabetes, and branched hydrocarbons is used in heart transplants to check on the rejection of the organs after it is implanted. So as you can see, this cannot only be used for to know if the air is polluted, or if the apples are ripe, or if the wildlife is in the mating season, but it has also been quite used in medicine and can be used, for instance, as lung cancer marker. And that was our idea when we started doing this. We were doing this with the Lung Cancer Portuguese Institute. Nowadays they have been training dogs to smell people, and the fact is that the dogs have how should I say, a failure rate of only 5% when they smell people for lung cancer. And so this means that there are some volatile compounds in your breath. There are some volatile biomarkers that can be identified by dogs. And we were looking for those types of compounds. Okay, so we did 4 approaches to this. We call them thick, thin, particles, and porous. So the first example that, and then we want to move around from one to the other. So first we prepared the thick, very similar to the gas separation membranes. Then we prepared the thin and checked for some differences between the thick and the thin, because when we have a very thick layer, we sorb a lot the compounds inside of the layer, like for instance here, but then in the GC they are not able to come out. There's not enough time for them to come out. So we needed to have a thinner layer, and then we did a thinner layer. And then we started thinking that probably we could go to much lower limit detection, because if we prepared some porosity inside of the membrane, so that it would, by having a high surface area, would sorb much more analytes. So our first approach was to use particles. So we just grinded the polymer particles and glue it to our sensor, the tip of our plunger. And the last work that we did, it was really to have pores inside of it. And I'm going to show you how we use this. Okay. So the thick coating preparation, what we did is this reaction that, as Tamal was saying, is by ring closing. It's a ring closing reaction. We did this with UV light. And so we were able to prepare a series of pyrrolidinium TFSI polymers. We checked here if everything was going okay in the NMR. and everything was fine. And here you also asked me about DGA and DSC, and this is for DNTF2. So we can see here the melting points and the glass transition temperatures that are much lower room temperature. Okay, so that it does not melt inside of our GC. So this is the way that we prepared it. We had a mold. We filled the mold with the polymer inside. We put the plunger in, and then we took it to the UV light. And then in the end, we took out the mold that was a glass mold with HF. And this is how we got our plunger prepared with the polymeric ionic liquid. So we rehearsed a couple of lengths, alkyl chain lengths in our polymers to see if we could detect alkanes. At that point of time, it was told, they told us that typically what people exhale when breath analysis is taken in people that have lung cancer. So they have breath bags, and people breathe into bags, and then you analyze it. There are a lot of long chain hydrocarbons. And so this is what we wanted to attract. It was long chain hydrocarbons. Here we have the fiber. This is non-coated, this is coated. And so you can see that we have 67 micrometers of thickness of our coating. We use these coatings. We use these coatings to sorb and desorb complex matrices, because we wanted not only to see the long chain hydrocarbons, but also a variety of other compounds. In fact, these fibers were so dense that we could not see long chain hydrocarbons, but we could see the other compounds. The matrix that we here used, it was not breath, but it was urine that it was spiked with these compounds. Here we have the comparison of our fibers against the commercially available fibers. So what we have here is, this is the total peaks area. So if I sum up all these peaks independently of what they are, we can see that we have a very low limit of detection here on the polymer that has C14 chain. And here what we can see is that we can, with these polymers, we can detect very well alcohols, menthol that is an alcohol, terpenics like camphora, citronellol, and so on. Smaller compounds, more polar compounds were not very much sorbed by our fibers, but you can see that we are always, or most of the times, doing much better, especially with this C14 fiber, than the commercially available fibers that are the yellow and the blue that are here. So these are these were very interesting results. We did more than 100 injections with the same fiber. So we sorbed and desorbed more than 100 times. And the fibers are very reliable and with a repeatability between 6 and 17%, which is normal for these types of fibers. However, as I told you, we were not happy with our performance with the thick coatings, because it took a long time to desorb the analytes inside of the GC oven. So we thought about preparing some thin coatings. And to prepare the thin coatings, we also thought that we had a very, the polymer was very, it had a very dense structure and not enough free volume, and did not allow the compounds to dissolve and be removed from the structure. And so we decided to design some other polymers and to synthesize some other polymers that had a benzyl group and a imidazolium group, again with the NTF2 anion. And what we have done, it was to use an airbrush just to coat the plunger while we spin it in a temperature-controlled room that we built specially for this. And here are the results of our thin coatings. We can see that we decreased from 56 to 10 micrometers. And the results. So here, we thought that as we have here so many aromatics, that we should go for the BTEX detection. As you all know, BTEX compounds are constitute one of the contaminants from like oil spills, lubricant spills in the sea and in the soil from the pumps. They are also present in cigarette smoke. And so we thought that it should be interesting to test. In this case, in the other case, we spiked urine. Here we spiked soil with these compounds. And these are the results that we got. In this case, we used PDMS because the chromatography supplier said it was the best one for us to do BTEX. Was PDMS. And we can see that we have some compounds that it absorbs more than other compounds. We can see that typically we do better than the commercially available fibers. And so again, we did more than 1/100 injections. And we think that this high detection limit is due to the lots of aromatic groups that we have introduced here inside of our polymers. Nevertheless, when you look at the results, we did this here with an ethyl group, here with a benzyl, and here with a chain. The one that absorbs the most is the chain, and we think that it's due to free volume effects. Okay, so the next one that we did, we still wanted to go deeper inside of these, deeper in the sense that go low on the detection limit. And so at that time, we did not know we were exploring how to do polymers with pores. And so what we decided to do, it was to grind the polymer and just to glue it with silicone to the plunger. And that's what we did. Here we have the plunger with the particles. We can see them here, so we just grind them. And we did not use a molecular sieve. And we have very heterogeneous pore sizes, particle sizes, and we really wanted to have that so that the particles would not colmatate in the surface of the plunger. And here we can see all our particles glued to the plunger. This film that I've created now has 25 microns of thickness, and it's constituted by particles that are mainly between 2 and 10 microns. So we used one polymer from the other group of polymers, the one that had the benzyl here as a substitute in the imidazolium ring. But we played around with the anions. So now we have a bromide here, and we have TFSI also. Okay, so comparing our three polymers, which are the three bright colors here, we can see that the bromide anion really performs very well. And second, it is the TFSI. So both of these polymers perform better than the pyrrolidinium polymer, but all of them perform much better than the commercially available fibers. We did this, let me put it all, we did this for alcohols, so from ethanol to octanol, and try to see which one was the best. Here in this case, we did it again for BTEX, and for BTEX now we have a very good sorption of ethylbenzene with the TFSI anion. So it really depends, as you can see, when we have very complex samples, we have alcohols mixed with aromatic compounds. One fiber works the best for one compound, and another fiber works best for another compound. So you really have to come up with a very efficient fiber that can give you the entire spectrum of our sample. We did a very case study, also a very interesting example in a case study, which was to, everybody knows that smokers exhale benzene and toluene, and also in their urine there is benzene and toluene. And so what we've done, and these are samples, non-spiked samples from real people. So we went around the lab, the labs in our floor, and we collected urine samples from smokers and non-smokers, and we tried to detect these compounds, benzene and toluene, in the samples. And here are the samples. So the green are the non-smokers, and the brown are the smokers. And what we can see here is that the commercial fibers, DVB with carbon and PDMS, so now this is a very new fiber that just came out, that is a mixture of polymers and it also has activated carbon in it, does not detect as well the amount of benzene and toluene as our fibers do. So we can see that here, just by applying this proof of concept in natural matrices, that our fibers really. Last but not least, I want to show you what we did for the preparation of porous coatings. I believe that the preparation of porous coatings is going to be very important in a lot of applications. This part is analytics, but I think that they are going to be very, very important in gas separation, for example. So what we did is we prepared a polymer, and here when we prepared the polymer, we functionalized the imidazolium group. We functionalize it with the cyano group. So here is our polymer that has a cyano with, that has an imidazolium with the cyano group. It's again a TFSI. And the way that we prepare the fiber that is here, it was first, before doing the coating of the fiber, we just placed it in acetic chloride acid for 20 minutes to clean the fiber and scratch the fiber so that the polymer really adheres to the fiber. Then we had a mixture of our polymer, the polymeric ionic liquid, and the polyacrylic acid, and we just deep coated our fiber. And then we placed this fiber inside of an ammonium solution in water, and this ammonium solution changes the polyacrylic acid from the neutral form to the charged form and desorbs it from the matrix, desorbs it to the water. This is an aqueous solution. And in 4 hours, what it happens is that the polymer, the polyacrylic acid, is all dissolved, and I get a porous fiber. So with a much higher surface area that can, in a small time interval, absorb much more compounds. These are the looks of our fibers and the optimization. So here we are optimizing the amount of time that we need to leave our polymer inside of the ammonium solution. At 0 time, we are like this. You can see that if we take it, if we put it by 1 hour inside of the ammonia solution, we can see the pores starting to come up, but still they are very small. And this is after 4 hours of our plunger being inside of the ammonia solution. So here you can see very well the thickness of the coating. And here, this is the fiber, the plunger. And this is how our coating looks like. So this is what happens. We have a porous structure. This porous structure, we created it with 178 nanometers of thickness. And so it is really, really thin. So here are examples of the polyacrylic acid complexed with the polymer. And then here is the porosity measurements, the size of the pores that are around 200 nanometers. Okay, so here we did a very complex matrix in the lab. And again, we use this commercial fiber that has just come out, and it's known to be especially good for everything because it has the carbon inside, the activated carbon inside. And we compare the porous with the non-porous. We can see that this is the difference that the porous make. So without the pores, we have the green, okay? With the porous, we have the red. So these are very interesting results. And the blue is the commercial fiber. So we can see that for some compounds we are doing equally well, for some there are some compounds that we are not doing still as well as the fiber, like these ones here, more towards heavy terpenes. But in the alcohols, we do them very well, and the heptane and the hexane and the other hydrocarbons, we can also sort them very well. Okay, so conclusions also from this part. So these were this work on SPME extraction phases based on polymeric ionic liquids was very nice, ended up in a very nice part, having all these pores. The pores really help in the extraction, but we need to tune the cation and the anion of the fiber in order to have selectivity. We saw that quite well in everything that I presented, that either the functionalization on the polymeric ionic liquid or the anion are very important to tune the fiber to sorb some specific materials that we wanted. Okay, and this is it.
Okay, thank you again. So, any questions from the audience? So
No questions? Or is
I
somebody...
will find out questions. So, yeah. Let me thank Professor Maruko now for including lecture. It was wonderful to have you participating in this and delivering this talk. in this particular short-term course. You have carried out a variety of different applications, starting with the basics about the ionic liquids and eutectic solvents, which is, I'm sure the participants have got enough knowledge. And then you have covered the extraction, then the separation of carbon dioxide, and finally you concluded by the solid phase micro extraction. So once again, I thank you all, and especially Professor Maruko for delivering the talk. So she would be available if you have any queries still after this lecture. You can obviously mail her. She will respond to the appropriate query. Okay, thank you. And you want to add anything, Professor Maruko? You can add.
Now, I just want to thanks for organizing this seminar. I think that in times like those that we are living today, that we are very much isolated, it's very important to continue to talk with our students, to talk with our colleagues, and these seminars do make a difference. There's not there's no conferences that I know that have been agended so far for this year regarding the Ionic Liquids conferences. And so it is always a pleasure to participate in these seminars because they are very important to keep us together. Thank you so much.
Thank you. Thanks a lot. Thanks. Okay, so so we move to the next lecture. So next lecture will be from our institutes, IIT Guwahati, and this will be presented by Nabendu Paul. I'll ask Nabendu Paul to share his introduction and share his first slide. So he will be talking about on the molecular modeling strategies for hydrophobic eutectic solvents. So he's a senior postgraduate student of our department, and he is also working in the field of ionic liquids, especially the pharmaceutical extraction and also its remediation. He has already undertaken work related to molecular dynamic strategies, and he will discuss that in front of you. Yeah, so I'll ask Navendu to kindly share his screen or his slides.
Thank you, sir. Is the slide visible?
Yeah, it was visible.
Okay. Okay.
But now it's not. That's fine. That's fine. Yeah.
Okay.
Do it in a full screen.
Yeah, it is now in full screen.
Yeah. Yeah. Please go ahead. Yeah.
Thank you. Good evening, everyone. Here I am presenting in the Spark Symposium organized by the Department of Chemical Engineering, IIT Guwahati, and my topic of discussion today is molecular modeling strategies for hydrophobic eutectic solvents. Before starting my presentation, I'd like to show you where our campus is located actually, the IIT Guwahati. It's located here. It is the world map, and you can see India's map here. And IIT Guwahati is located in the northeastern part of India in the state of Assam. It was established in the year 1994 and it is recognized as an institute of national importance by the government of India. It is often cited in the media as the most beautiful college campus in India due to its natural and scenic beauty. It is covering around 700 acres area. And also it is ranked among top 10 institutes in India, in NIRF, QS and Nature Index, and among top 500 institutes in the world by QS and Nature Index. So There are some pictures of our campus, IIT Guwahati. You can see the natural beauty. It's very beautiful campus, and so I'd like to invite you all visit at least once in the campus of IIT Guwahati.
Yeah, the slide has not changed. Dabendu.
Now, sir.
Yes, yes. Now.
Okay. So, yeah. So let us start with the talk today. That is on the Eutectic solvents. So I won't cover broadly about what Eutectic solvent is because Professor Isabel has already discussed it quite elaborately. So I'll just give an introductory part of this. What Eutectic solvent is? The Eutectic solvents actually are the mixtures of two or more compounds, in which one is termed as the hydrogen bond donor and others can be termed as hydrogen bond acceptors, and they combine together to form liquids in room temperature. So here is an example of a Eutectic solvent which is prepared very early, around in the year 2004 by Abbott. So here choline chloride and urea are used as the hydrogen bond acceptor and hydrogen bond donor in the molar ratio of 1:2, and choline chloride urea Eutectic solvent has been formed. Among the Eutectic solvents have various properties, which among them some are low volatility, non-flammability, non-toxicity, biocompatibility, and biodegradability. So due to all those properties, it is extensively used in various applications and in various fields. But as my focus is in the area of wastewater treatment, the wastewater treatment of the micropollutants or pharmaceuticals from water with the help of Eutectic solvents. So I need to find some hydrophobic Eutectic solvents for my work, and also I need to understand their properties in the aqueous medium, and also how they extract or what is the extraction property of those DESs from water, like how they extract the micropollutants and pharmaceuticals from water. So for that, experimental studies and are very useful, but they are quite expensive. The experiment, and also the time, it is very time consuming. So for that, molecular dynamics simulation can be an effective tool to solve that problem and to understand the behavior, or to predict the behavior of different systems. Here are some examples of hydrogen bond acceptors and hydrogen bond donors. These are widely used in the DESs. Here you can see that there are menthol is present in both hydrogen bond acceptor and donor. It means that there is no certain hydrogen bond acceptor and donor in this field. It depends on the components that you use. The components that you use as the hydrogen bond acceptor and hydrogen bond donor, it determines whether it will donate or it will accept the hydrogen bond. So it actually depends on those components and the ratio that you are mixing them. Here is the overall molecular dynamics simulation setup and steps. So what we do, first we initialize the coordinates with the help of some force fields like charm, OPLS, amber, and chromax. So in my case, I am using amber generated force field to generate the force fields and topology. After that, and we use PackMol software for packing the systems. After that, we go to the MD steps, among which the first one is the minimization step. Here we minimize the potential energy of the system. We give 0 Kelvin as a temperature to minimize the potential energy of the system to a minimum. And then after that, we assign some it assigns some velocity, initial velocities, and goes to the heating step that is desired, because we need to do the experiments in a certain desired temperature. So we need to go from 0 Kelvin to that desired temperature. And here I am, in our case, it is 298 Kelvin that we are doing all the experiments. So in this case, the NAMD 2.1 we are using for the molecular dynamics simulation. So MD simulation starts from this minimization actually. And after that, we go for the equilibration step. Here we can use NVT or NPT ensemble. Like NVT means number, volume, and temperature. Number of molecules, volume of the system, and temperature of the system. And NPT means number of molecules, P means pressure, T is temperature. So NVT, in NVT, the N, V, and T of the system is constant, whereas in NPT, the N, P, and T are constant. So in our case, our equilibration step, we use NPT ensemble. We keep the pressure constant so that the volume gets changed. The variable volume can come into place and give us an optimum or equilibrated box size actually. So after that, we go to the production dynamics, the production step where we maintain the system for like 5 to 100 nanosecond of production run, and we in our case we are using NVT ensemble in the production run, and after that we get the trajectories and we analyze the trajectories in VMD or Travis software to get some dynamic and structural properties like diffusivity, interaction energy, hydrogen bonding, and all those. So moving on, this is the overall MD simulation methodology, like what we do exactly in our case. So first, we use Gaussian 9 for optimization of the structures and ISP charge calculation, the restricted electrostatic potential charge calculation, in which we use DFT Bithrelief method and 6311G plus TP basis set. After that, we use the anti-chamber module of Ember 14 to get mole 2 all the molecules in our desired composition in pack mode. After packing, we get the packed system box, which we do MD simulation in an MD 2.1, and after certain minimization, heating, equilibration, and production run, we get the trajectories, the final trajectories, from where we calculate the properties, the interaction energy, RDF, radial distribution function, combined distribution function, hydrogen bond, diffusion coefficient, and MST plots, etc. So what are the objectives of the present study that I am going to show? There are 3 objectives. First, the molecular dynamics study of the stability of some hydrophobic Eutectic solvents in presence of water. We are the hydrophobic Eutectic solvents are not totally hydrophobic as it is termed. So in my case, the wastewater treatment, I need to find a very hydrophobic Eutectic solvent. So for that, the stability analysis is very important in my case. The second work is after getting a suitable solvent, hydrophobic solvent, let us go for the extraction of some pesticide or some pharmaceutical. So here I have selected nitinpyram pesticide to extract from water with the menthol based DES. And after that, the third one is using similar Eutectic solvents to separate the organosulfur compounds present in the fuel oils. And this is the quantum chemical study that we have done in the organosulfur compound separation. So here are the overall graphical presentation of my work. That is, we have used HBA as DL menthol and tetrabutyl ammonium chloride, whereas HBDs are a different combination of organic acids ranging from acetic acid, butanoic acid to dodecanoic acid, like C1 to C12 of chain length carbon. So this is the stability part, stability analysis of Eutectic solvent in water. And after that, in the right side, I have used the L-menthol and octanoic acid based Eutectic solvent to extract nitinpyram, which is initially present in water, and later this is done with the help of MD simulation. So here is the composition of each and every system that I have prepared and I have executed the MD simulation. Here the 1:1 mass ratio of DES and water is maintained for all the systems. So here you can see that the periodic box size that is in the right column is different for each and every system. It is because we have given an ET ensemble in equilibration, and it gives us the equilibrated periodic box size. Like it maintains the density of the system, and it gives us the equilibrated box size for all the systems. Here I have shown the number of molecules that I have initially taken in our system. So here one thing needs to be mentioned: for the first 8 systems, the HBA is constant, that is the DL menthol. I have only changed the HBD, the hydrogen bond donor, from acetic acid to higher organic acids like dodecanoic acid. And system 9 and 10 is tetrabutyl ammonium chloride as HBA, and acetic acid and octanoic acid respectively for HBD. So let us go to the results and discussion part. The first result that needs to be observed is non-bonded interaction energies of all the components, which is in the kilocalorie per mole unit. Here I have segregated these systems, and the total non-bonded interaction energy is divided into 2 parts. One is electrostatic interaction, the second one is van der Waals interaction. So here we can see, if we see that the menthol water and menthol acetic acid menthol acetic acid system, for the S1, system number S1, we can see that the electrostatic interaction is less than the van der Waals interaction for the HBA and HBD. That is 1.72 is less than 2.48. Whereas for HBD water interaction, acetic acid water interaction, the electrostatic part is higher than the van der Waals part. That means that the acetic acid is interacting with water more electrostatically than the van der Waals, because the acetic acid is the size is very less, so the water molecule can easily get to the acetic acid and it can create some electrostatic interaction. But if you notice the HBD water for all the systems, if we gradually increase from acetic acid to butanoic acid, hexanoic acid, and octanoic acid, you can see the total non-bonded interaction, which was 3.17 in case of acetic acid, is gradually decreasing, and it is gradually decreasing to 2.94, 2.55, 2.4, and 1.9 in case of decanoic acid, which means that in the presence of water, the butanoic acid or acetic acid, the less number of carbon chain carboxylic acids are much more water miscible than the higher organic acids, because they have high hydrophobic property. The higher organic acids have high hydrophobic property, that's why they repel water. Whereas if you see the HBA HBD part, that is menthol acetic acid, and compare for all the systems, you can see that for acetic acid is 4.20, but butanoic acid it is increasing 8.09, then 11.47 for hexanoic, then 12.52, 13.96. It means that the menthol, HBA, and acetic acid or organic acid, like organic acid HBD, if we increase from lower to higher chain, large number of carbon atoms, so the hydrophobic tail is increasing, which repels water. But at the same time, the integrity of HBA and HBD is increasing. Like the interaction is increasing between HBA and HBD, which means that the DS integrity is increasing, is improving when we move from acetic acid to higher organic acids. Another thing, for the system S1, if you look closely, you can see that the total non-bonded interaction energy for acetic acid water, which is minus 3.17, is very close to the total interaction energy of menthol acetic acid, that's it, HB and HBD. So the formation of eutectic solvent here, menthol and acetic acid based eutectic solvent, is the acetic acid water interaction is challenging that formation of eutectic solvent. That is, after mixing with water, the DS integrity is completely lost, or you can say 60 or 80% lost after half an hour or 1 hour of mixing. So that so we cannot say that these are hydrophobic eutectic solvents. We cannot use those eutectic solvents for our extraction from water or something like that. Let us move to the other systems. Similar tendency is shown. So menthol dodecanoic acid is the highest water stable that we have found, because the non-body interaction energy between HBA and HBD is 22.87, which is the highest, and the dodecanoic acid water interaction is very low in comparison to the HBA HBD. So we can say that the interaction energy suggests that higher organic acid is useful for hydrophobic to make hydrophobic eutectic solvent. Also, we have done some studies with pyruvic acid and levulinic acid, two keto acids, organic acids, to show whether these are hydrophobic or not. But these are showing good HB HBD interaction, but the HBD water interaction is also quite higher. So the integration of DES is not properly maintained. So we cannot say that these are hydrophobic. These are water miscible. When we come to system S9 and S10, that is containing tetrabutyl ammonium chloride and acetic acid as HBD, whereas octanoic acid is other HBD. Here the HPA is constant for those, same. Here also we can see that the acetic acid water is quite miscible, but here another thing is that the N44Cl, that is cation, the HPA is very much water soluble here. In the case of menthol, it was not that much water soluble, but in case of N44Cl, it is quite water soluble, so it is disrupting the characteristic of the DES. So overall, we cannot say that these two are also hydrophobic in nature. So let us move to the next part. What we got from the interaction energy study. We got the total on-body interaction energy between HBD and water gradually decreases from moving from acetic acid to higher organic acids like dodecanoic acid. Whereas the hydrophobic tail actually of the HBD molecules, which is ranging from CA to C12, from octanoic acid to dodecanoic acid. In those cases, the hydrophobic tail, the large hydrophobic tail, pushes the water molecules due to steric hindrance, and for that the water molecule cannot come in close contact with those HBD molecules. Also, the electrostatic interaction between the HPA and HBD is less dominant than the van der Waals contribution, which means that the entropic effects is predominating than the electrostatic effects. The fourth one is the hydrophobic property of the individual components determine the overall stability of the eutectic mixture. What does that mean? That is, for having a proper hydrophobic eutectic solvent, you need both HPA and HBD to have strong hydrophobic properties. Otherwise, the eutectic solvent will get disrupted in contact with water. So, from the whole study, can we get some qualitative idea with the quantitative data that we have? So we tried that one to get some qualitative idea with those quantitative data, and we have created one relative stability factor that we have come across. The relative stability factor of hydrophobic eutectic solvents. What does that mean actually? It means it is actually the relative measure of the stability of a hydrophobic eutectic solvent in presence of water. So it is actually the ratio of the interaction energy of HBA and HBD divided by the combining interaction energy of individual components, that is HBA water and HBD water. So if we do that, and with some experimental studies done by Professor Isabel's group, so we found out that from 0 to 3.3 of the stability factor, it is miscible in water. Let me show the chart. This is the chart that we got from the stability factor analysis, and these three systems, these three eutectic solvents are hydrophobic in nature or water stable in nature, whereas the other eutectic solvents are not stable in water. So from that we can say that the octanoic acid, decanoic acid, and dodecanoic acid has higher stability factor, which makes them stable in water. In case of ammonium chloride-based depurated solvents, both the acetic acid and octanoic acid based depurated solvent, they were unstable in water. So overall stability, if we say that if we analyze the stability by the relative stability factor data, we found out that the higher chain organic acid is much more hydrophobic than the smaller chain like organic acids. So let's move forward. So these are the distribution snapshots at 0 and 100 nanoseconds respectively for each and every system. That is 10 systems. Okay, the blue colored molecules are the HBA molecules. The yellow colored molecules are HBD molecules. And the red one are the water molecules. Here we can see that initially, what we have done initially, we have kept the HBA and HBD, that is the TES, separately than water. See here, the water is in another phase than the DES. And after that, we gave 100 nanosecond of production run. And what we found out after 100 nanosecond of production run, that the yellow, that is the HBD molecules, were quite interacting at the least, interacting with the water molecules. Mainly the water molecules reached to the DES phase to disrupt the HBA HBD integrity. So similar things were observed in case of acetic acid system, butanoic acid, and hexanoic acid system. Here the HBD mainly is interacting with the water, but the order is decreasing. The range is decreasing from acetic acid to hexanoic acid. When we observe the octanoic acid water system, we found out that the water is in separate phase after 100 nanosecond of simulation run. Here we can clearly see that the water is still in the other phase than what is present initially. So from here, the hydrophobic nature or the stability is starting. And after that, decanoic acid and dodecanoic acid is showing similar results, which in case of dodecanoic acid, it is improving. The hydrophobic nature is improving. But when you go again to the pyruvic acid and levulinic acid systems, you can see that it is again disrupting. The water is disrupting the DES systems. These two systems, S9 and S10, are the tetrabutyl ammonium chloride based systems, in which in one acetic acid is the hydrogen bond donor, in other octanoic acid is the hydrogen bond donor. So here we found out that the TPA, that is tetrabutyl ammonium cation, is also interacting with the water along with the acetic acid. In case of DL menthol was not interacting with water, but in this case, all the components are interacting with water, which is completely disrupting the system. But in case of PbACl octanoic acid water system, we found out that only the cation and chloride ion, PbACl, is interacting with water, not the yellow one, that is the octanoic acid. So it shows that the individual components' hydrophobic nature is very important in maintaining the DES quality or DES integrity. So this is the radial distribution function analysis. So before analyzing, I should talk something about the radial distribution function and what it is. The radial distribution function is the probability of finding a particular atom or molecule at a distance r from another atom or molecule, that is the central atom. So what it signifies that we have a central atom here, the green one, and around the green molecule or green atom, the other molecules or other atoms, they are coming close to this and having and making a coordination shell or solvation shell. That is the interaction of the central molecule to other molecules. So here you can see that the first coordination shell and second coordination shell. In the first coordination shell, the peak is very high, which signifies that there is a high presence of those those other molecules in close to the green one or the central molecule. However, after certain distance, another distance, we found another shell, that is the second coordination shell, which means that after certain distance, the correlation function of the central molecule to the other molecules is still not diminishing. After some certain distance, it has some correlation with those molecules after some distance also. But as we move forward to outer radius, it after some time it finds the continuum, that is no correlation is there between those central molecule and the outside molecules. So from radial distribution function, we can find out the presence of the molecules or atoms in the vicinity of a certain molecule. So it can also signify the interaction. It can also signify the interaction of the molecules with the central molecule. So in the right side, we have calculated the dodecanoic acid DL menthol radial distribution function. That is the HBA and HBD interaction. So here you can see that around 2 angstrom, it is having a higher peak, and after that around 4 angstrom, it is having a lower peak, and then it continuously goes to and attains the one value, that is no correlation is there. So here the first one is the first solvation shell and the second one is the second solvation shell. This is between the HBA and HBD molecule of the dodecanoic and DL menthol based DS. So here the comparison study of the RDFs that I observed in my system. Here we have compared here the acetic acid, octanoic acid and decanoic acid based systems with water for each system. And we found out that the acetic acid has the highest peak in comparison to the octanoic and decanoic acid, and which signifies the similar thing that we found from interaction energy. That is, the interaction between water and acetic acid is much more higher than the other HBT and water, which makes the acetic acid water very much miscible to water, which is which disrupts the pH integrity. Also, another thing, you can see the trend to get the continuum. Here, after certain point for octanoic acid and decanoic acid, the blue and the red one, you can see that it is having a close value to 1 and it is getting to 1. But in the same radius, the octanoic acid is having much more value, much more of the probability of having water molecules in the vicinity of them. So which means that the correlation function is higher in case of acetic acid water than the octanoic acid and decanoic acid. In the right side, here we have done the RDF analysis for the HBA and HBD. That is, DL menthol is same for every system. Only the HBD is different. That is acetic acid to decanoic acid. Here also we found out similar things. The decanoic DL menthol is having much more interaction or much more probability of finding one another in the around 3 angstrom distance. The radius is same for like every system, but the probability is different. The GR value is different for each and every system, and it follows the trend, the similar trend that we found previously. The decanoic is highest, then octanoic acid, then butanoic, then acetic acid is very less. So you can say that decanoic and octanoic is having more hydrophobic properties or higher interaction among the HB-HBT than acetic acid and HBA. So these are the continuation of the RDF for other systems. These are for system S9 and S10. The S9 contains tetrabutyl ammonium chloride and acetic acid with water, whereas system 10 is having tetrabutyl ammonium chloride with octanoic acid and water. So system S9 contains acetic acid, S10 contains octanoic acid. In this, you can see in the figure D, figure D, you can see that the acetic acid is having higher interaction with water than octanoic acid, and due to this the cation, the TPA cation is having less interaction with water, because the water molecule of the S9 system is having so closely interacted with the acetic acid molecules that the TPA molecules are not getting enough water molecule to interact with. Both have similar, TPA has similar interaction with water in both the systems, but here you can see that the TPA in system 10, that is containing octanoic acid, is having more interaction than the TPA in acetic acid system. Because acetic acid is having more interaction with water, so less amount of water is present for TPA, so it is having less interaction with water. You can see the figure B here. It is the HPA and HPT. Both have similar interactions. Negligible difference is there, so this is no problem. But here in the C plot, you can see this is for water and chloride ion. We know that chloride ion is miscible is interacting with water, but it is the amount of interaction or the probability of finding this chloride ion in the vicinity of water is so high. It is having 18 or 14 GR value. So the chloride ion is much more interacting with water, which means that the TBA cation and chloride ion anion is having less interaction, which means the TES is already disrupted, because each of the components is having more interaction with water molecules. It is the significance of this RDF plot. So let us move to the other structural property of the analysis of our system, that is the combined distribution function. So it is by the name of itself, it is suggesting that it is combined. So it is combining radial distribution function and angular distribution function. From the radial distribution function, we came to know the distance in which the molecules are surrounded. But but from angular distribution, we know that exactly at which angle these molecules are getting interacted or getting aligned. So overall, combiningly, it is giving us a pinpoint value where the presence of those molecules are. So in here, you can see the alpha value is the angle between the interaction, that is the bond, and the R value is the radial distance, that at which distance it should be found. So in the right side, you can see that here are some combined distribution function analysis of our system. So you can correlate this with the RDF value that you have found. So let us go back. First we see that acetic acid water, it is coming, see the interaction, the blue part and the red or yellow part is coming around 300 picometer, that is 3 angstrom. So if we go back for acetic acid water, this is the acetic acid water at which R value we are having the peak. It is around 3. You can see. So it should come at 3 interaction also. So we can see that it is coming at around 3. And in here you can find the angle of the distribution. So it is having like distributed value of angles. You cannot say that it is this much angle. So it is having a combined effect of all the molecules, and it is having a distributive angle. So let us go to the next B, that is decanoic and DL menthol. So DL menthol, that is HBA, and decanoic is HBT. So we expect good interaction between them because they are HB and HBT. So here we can see that the interaction is coming around. It is also coming around to 3 angstrom. So let us go back to the RDF, DL menthol and decanoic acid. So let's see here, the decanoic acid and DL menthol, the blue one is coming at 3 angstrom. So we are having same values. So let us go to the angle Here the angle is distributed from 100 to around 160. So it might be an effect that there might be the presence of hydrogen bonding, which is for which the criteria is around 3 angstrom of distance, angstrom, and the angle should be greater than 135 or 140 degree. So it is in that range. So we can say that there might be the presence of some hydrogen bonding within those, which is the basis of the deep eutectic solvent formation. Let us go to octanoic acid and water. We are showing all the components can how their combined distribution function appears. So octanoic acid water, we know that there is very less amount of interaction between octanoic acid and water because it is hydrophobic in nature. And so in this case also, in this PDF also, we are having this similar kind of results because there is no such interaction that is shown in this So let us move to the octanoic acid and DL-menthol. This is similar to the decanoic acid and DL-menthol. These are also coming in the same region, 303 angstrom, and having some values of angular distribution. So we can say that the DES is intact in those cases, whereas for acetic acid, the DES integrity is not there. Let us move to the next part, that is hydrogen bonding analysis. So, these are the components that are present in all the systems, and we have calculated the average number of hydrogen bonds that are present in the system throughout the simulation time from 0 to 100 nanosecond. And we see that the trend here is, you can see hydrogen bonding between HBD and water we have calculated in A. So HBD and water, so we know that water is having higher interaction with acetic acid, so it will be coming highest. Acetic acid water will be coming highest for the H bonding analysis, and it is following the similar trend. First the acetic acid, then it is coming levulinic acid, after that butanoic acid, then hexanoic acid. So it is following the similar trend that we found in interaction energy, which supports that the DES integrity in case of acetic acid, butanoic acid, pyruvic acid, and levulinic acid can be disrupted due to the higher number of hydrogen bonding present between, or hydrogen bonding formed between the HBD and water molecules, for which the interaction is also higher for between HBD and water molecules, and which in turn give us the idea that the DES molecules, why the DES molecules are disrupted in the aqueous media. Let us come to the HBA and HBD interaction now. So we know that acetic acid, DL-menthol acetic acid interaction is lower, and as we increase the chain length of the carboxylic acid from C1 to C12, we will be having a large interaction or higher interaction. So similar thing is coming in the H bonding also. The average H bonding of the DL-menthol dodecanoic acid is the pink one is the highest, whereas the DL-menthol acetic acid is coming at the lowest. So it is the similar trend that we have noticed in case of hydrogen bonding also. So this is the mean square displacement. It is actually the transport behavior of the components within the system or within each other. How the components are transported within the phases. There might be presence of two phases, and how the components that are present in the system can transport from one phase to other. It is the we calculate this from the mean square displacement analysis. So it takes the Einstein's equation of self-diffusion coefficient into account, in which this is the equation where the bracketed part, that is this one, the bracketed part is considered as the mean square displacement of the molecular species, and the slope of this curve actually signifies the diffusivity of the components in the phases. So if we look closely into those graphs, this A and B is for the acetic acid system, and C and D is for octanoic acid system. The first one is for 0 to 10 nanosecond, the first simulation run, and the second one is for 90 to 100 nanoseconds. So as to compare whether they are distributed, how they are distributed. So let us see the A and B, that is acetic acid at 0 nanosecond and acetic acid at 90 nanosecond. You can see that it is more of a similar kind of trend. It is initially having this arc, and after 100 nanosecond of run, all of them quite close to each other and also having similar kind of interactions. So it means that the components present in the system are diffusing at a similar rate. That is, they are interacting with each other. We can say that from this graph. But if we come to the C and D plot, we can see that the water, that is blue one, is initially present, and the DL methyl and octanoic acid is transporting at a different rate, is diffusing at a different rate. But after 90 nanosecond or 100 nanosecond of run, still we found out similar trends. That is, over the simulation, entire simulation run, the transport behavior didn't change for all those components. That is, they are maintaining, the DL menthol and octanoic acid are maintaining similar trends to each other and different from the water, which signifies that the distribution is quite different, the diffusion is quite different, and also water is not distributing to or diffusing to the DES space. That is what we can get from this this data. So let us move to the second objective. We have performed the stability analysis, and we found out some diffusive solvents that can be used in case of extraction. Which one is DL menthol based DES with anionic, decanoic, and dodecanoic. So we have selected one diffusive solvent from them, and it is DL menthol and octanoic acid based DES. So here you can see the distribution snapshot from 0 nanosecond and 100 nanosecond of simulation done. Initially, the red one is the drug, the gray and yellow is the DES, that is HBA and HBT, and blue one is the water phase. So initially the drug was present in the blue part, that is the water part, water phase. After 100 nanosecond of run, some drug molecules came completely to the DES phase. Some are stuck or have just crossed the interface, and some are still in the water phase. It signifies, or it gives us the idea that how they are separated, or how much of extraction can be happened with this kind of solvents. We calculated the non-bonded interaction energy here also, and we found out that the nitin-pyram octanoic acid interaction is higher than the nitin-pyram water, and nitin-pyram DL menthol interaction is also higher than nitin-pyram water. But here one thing is that the solubility of nitin-pyram is high in water than as compared to the DES, because it is having a higher solubility with water, which makes it difficult for the diffusive solvent. Though it has higher interaction, it is showing higher interaction, but still it is difficult for the interface for the drug to cross the interfacial barrier. Actually, that is what we found out in the extraction efficiency in case of in experimental as well as in the simulation. The extraction efficiency is closely 43%, and we got similar results in MD simulation also. So let us go to the analysis part here. The DS rich phase, we have calculated the mole fractions of each components in the DS rich phase and also the water rich phase, and then we calculated the distribution coefficient and the selectivity. Distribution coefficient is the ratio of mole fraction of the drug in DS rich phase and the water rich phase, which is coming 5.19, which is good. And also the selectivity is the ratio of the distribution coefficient in DS rich phase, DS, and in water. So it is coming 55, which signifies that the solvent can be selected as the extractor of the drug from water phase. We calculated the distribution ratio. The simulated distribution ratio came around 0.72, and the experimental is around 0.67, which is very close to the experimental result. So we can say that we can validate our results with that. So here also we have found out the RDF and CDF plots, and we can see that the Nitin-Pyram RDF, Nitin-Pyram distribution with DL menthol and water are similar, like the red and the blue are the similar. So which means that the Nitin-Pyram is closely interacting with water also, and also with DL menthol, which is the main reason due to its less extraction in the DS rich phase, because it is also interacting similarly with water. And if you see the DL menthol and octanoic acid HB-HBD interaction compared to the HBD water interaction, it is having similar trend. Like HB-HBD is having integrated, like the DS property or the DS contribution is integrated, or that it is not disrupted during the whole extraction process. So we can say that the hydrophobic depletive solvent can be used for the extraction of the solvent, but the extraction efficiency can be improved with selection of other HBD maybe. So here is the CDF, the combined distribution function plots, and as we have the here it is Nitin-Pyram with DL menthol. So let's see, Nitin-Pyram DL menthol is coming at around 2 angstrom. So here also we are getting some interaction at 2 angstrom, and it is having 160 to 180 angular distribution. So it signifies that there might be presence of hydrogen bonding between the Nitin-Pyram and DL menthol. Whereas in case of Nitin-Pyram and water, you can see at 2 angstrom it is having similar or high interaction, which signifies that Nitin-Pyram is having both similar kind of interactions with both the DL menthol, that is HPA, and the water molecules. You can compare the contour values, the plot values. So it signifies that menthol is having much higher. It is 754 and it is 414. So it is having a much higher interaction than water. But as I have said, the solubility of the drug in water is the dominant factor here, which is affecting the extraction efficiency as a whole. So this is the spatial distribution function. The spatial distribution function is the average density distribution of the components around a observable molecule or a central molecule. So how it works, like here we have a central molecule here, and we have other components in that system, and it shows that how the other molecules are distributed around that central molecule. It is similar to RDF and RDF, but it shows the exact density distribution. In RDF, we are just having some probabilistic value of whether there might be presence or not. So it is having some graphical representation here, and we can see which components are closely bound and which components are having interaction with the active site or something like that. So we prepared this. This one, the right one, is for our system. In the middle, the molecule that is showing is the Nitin-Pyram molecule, and we have performed the SDF calculation in Travis, and we got this kind of SDF structure, in which the blue one is the DL menthol, the yellow one is signifying octanoic acid, and the water is signified by this one, blue one. Green one is DL menthol. So we can see from here that water is having quite good interaction or good density distribution around this Nitin-Pyram molecule, then octanoic acid, and also then DL menthol, which signifies the similar thing which we found out in the case of extraction, which is less than 50%. So we can say that this drug is pesticide is hard to extract from water because it is having a good interaction with water. But we have obtained 40 to 45% of extraction, which is not bad at all for this case. Also, this is the average hydrogen bond analysis. You can see that the hydrogen bonding that we have observed in here is it's different from the extra interaction energies, like from the RDF. So in here, the methampyram octanoic acid average hydrogen bonding is higher than both DL menthol and water. Here, water is having less hydrogen bonding, but here the another thing is that the presence of large number of water molecules in the system. Though the number of average hydrogen bond is low, but the presence of large number of water molecules may make it overall a high number of hydrogen bonding with water. So which we expect from this kind of extraction, which is less than 50%. Let's move forward. Let us come to the third objective of us. Here we are separating, or we are using our MD's or quantum chemical study for separation of sulfur compounds, mainly organosulfur compounds, from fuel oils with the help of deep eutectic solvent. So here are 6 sulfur compounds that we have optimized: benzothiophene, benzothiophene oxide, benzothiophene dioxide, and dibenzothiophenone, dibenzothiophenone oxide, dibenzothiophenone dioxide. So organic solvents, the TS component that we have used in this particular study is this one. So the TS are methyl triphenyl phosphonium bromide and ethylene glycol, and this is one MTPBr, and ethylene glycol is one DS, and the other DS are menthol decanoic acid and menthol octanoic acid. And these two, n-heptane and octane, are the organic solvent that are generally used to separate these sulfur compounds from fuel oil. So, in this study, we have done the solvation analysis in Gaussian. The solvation analysis in this, we have what we did in the left side, the organosulfur compounds was initially present in the fuel oil, and they were extracted by the organic solvent, that is n-heptane or n-octane. So we are trying to find out another solvent which can transport these sulfur compounds from this organic solvent to that solvent, so that this organic solvent can also again be used, or this solvent can be directly used in separating the sulfur compound from fuel oil, because the problem is these have low volatility, high volatility. So these organic solvents have high volatility, so they will the pollution is also a phenomena in those solvents. So we need a green solvent to separate those sulfur compounds. That's why we are trying to do this study, whether the DS, the green solvent, can be used in separating these sulfur compounds instead of these harmful solvents. So one idea to do that is to know the delta G solvation, that is Gibbs free energy of solvation, and whether the difference is negative or not. From that, we can get the idea about whether these solvents can be used for separating this. So this is a cavity. This is a solvent cavity in which the solvent is present, and it is having certain radius of its structure. Okay, so this there is a cavity that is formed in a continuous solvent, and this cavity can be polarized by that the presence of this solvent. So in Gaussian, what we do is we use the SMD solution, that is universal solution model, to calculate the delta G of solvation, that is Gibbs free energy of solvation, and we understand whether the solvent can be used in separating this solvent, in separating these sulfur compounds. So these are the solvent parameters that are used in SMD solution process. So let me discuss something. That SMD solution process, we need to give some parameters as an input parameter to run the Gaussian optimization. These are the parameters: H bond acidity, H bond basicity, surface tension, dielectric constant. There is Ri, N is Ri, repetitive index. So N square is required. Carbon aromaticity and electronegative halogenicity. So all these properties needs to be calculated first. Then we need to input those properties, those variables in the Gaussian system, and then we run the assembly solvation. These things can be found out by experiments, experimental analysis. We found out these things. Carbon aromaticity is the presence of aromatic carbon in the system. It is the percentage of aromatic carbon present in the molecule, and the electronegative halogenicity is the percentage of electronegative halogen molecule present in the molecule. So only this MTPP or ETG, ethylene glycol, is having this value. Others are not having this value. So first we need to calculate this value, and we need to put this value as an input parameters. So let us see what we got from the assembly solvation. Here, these are all the sulfur compounds Bt2, DPTO2, and these are the organic solvents. And the first two is for MTPB ethylene glycol. The second two is for menthol dodecanoic acid, and the third two are menthol octanoic acid. So it means that the Bt, that is the sulfur compounds were initially present in those an heptanoctane or an octane, and these DESs in the right side were used as a solvation media, so that these sulfur compounds can transport to the DES phase. So we calculated the free energy of solvation, the energy of solvation for all the systems containing these sulfur compounds, and we finally got the deviation or the difference in free energy of solvation, and these are the values. So the red values are the negative values, which signifies that it can be favorable. These are the good results. So we found out that the menthol based DPTO solvents are not that much good in case of this extraction or the separation of sulfur compounds. Similar menthol octanoic acid DS was used in case of extraction of methane pyram previously, and we found out that it is quite good in extracting. At least 40 to 50% extraction was happening. But in this case, these values doesn't signify the results, like can we go for extraction of these sulfur compounds or not. So you can see that the selection of HPA and HBT is very much important in case of extraction or in case of any kind of application regarding DPTO solvent. Similar solvents cannot be used in every application. You have to find out which solvent or which component is better for each case. Here we can see that menthol based DPTO solvents are not good, but on the other hand, the MTPBR ETG is having good results, like 6.98, 5.48. These are good results for not for all the sulfur compounds, but a lot of four or three compounds that can be separated. That can be separated from these organic solvents. So we found out the changes in enthalpy also from the quantum chemical calculation, and we are having similar results. That is, DPP ETG is good for all the sulfur compounds, but menthol and menthol based DSs are not good for those extraction, for those separation. So overall, this conclusion signifies that the solvation free energy study, or the overall solution energy study, is implies that the MTPP ETG, like methyl triphenyl phosphonium bromide ethylene glycol, DS, can be used for the extraction of organic sulfur compounds, but menthol based DS are not good for this kind of extraction, whereas menthol based DSs are good for the extraction of pharmaceuticals or similar kind of products. The enthalpy and the energy changes both are showing similar patterns of the free energy study. And the future works in this study can be the to try different HP-HBD combinations for better results. So that concludes my work talk, and I'd like to acknowledge this is me. My name is Nabendu Paul, and my supervisor's name is Tamal Banerjee. I would like to acknowledge Professor Parthu Sarathi and Professor Isabel Marucho. I went to Lisbon for a brief period and worked in Professor Isabel Marucho's lab, and it was a good experience. I also acknowledge Spark for funding the project, and none other than this permission supercomputer, without which we couldn't do any simulation study. So thank you.
Okay, thanks Nabendu for the wonderful discussion, for the extraction of you have touched upon to our own group's work. Now this forum is open for any questions. We did have some questions on YouTube platform, which I answered there. If you have any other question, can you please raise the hand icon? Any other question? You can raise the hand icon. Okay, it seems so there are no other questions. So let me thank then Nabendu for the wonderful talk.
Thank you, sir.
And yes, and I hope that we will all continue with whatever Professor Maruko and has taught us for the last 2 days. So we conclude day 2 of our short-term course, and we now we go to the day 3. So day 3, the first lecture we will be starting tomorrow at the same time, 6 o'clock. So we meet, and there is a slight change in the first lecture tomorrow, which is my lecture. Since the current lecture, I saw Professor Maruko talking about the supported ionic liquid membranes, so which is quite similar to the next lecture, which I will also be talking a similar part of it. So I'll try to speak something else on ionic liquid, which is that is your chemical hydrides, right? I will try to see the hydrogen-based economy on chemical hydrides using ionic liquids. So that's what the change is. So we meet at the same time tomorrow at 6 o'clock. Okay. Have a nice day, all of you.
Thank you.
Thank you.